Our next topic in Chapter 17 is described as solubility equilibria. Solubility equilibria are the problems that we worked earlier called KSP, the solubility product constant for salts. It's asking us to question, if it dissolves, how much? Will it, and if so, how much? The KSP solubility product allows us to determine the amount of a salt that is dissolved per liter of water, known as solubility. Now, if it is a strong electrolyte, such as sodium chloride, NaCl, if I used my solubility chart, we would find that it is completely soluble in terms of solubility. What KSP has to do is with those slightly soluble salts, or if we're looking at our solubility table, the insoluble salts. Could we convince even just a small amount to dissolve into the water? So it's allowing us to calculate in moles per liter how much of a salt can dissolve in water. All dissolving is a process of equilibrium, dynamic equilibrium. So as sodium chloride is going into solution, dissociating to form its ions, there is a point where we reach something called saturation, that volume of water is holding as much as it possibly can in that particular temperature and volume. And what we would begin to see is an equilibrium setup where the dissociation in the forward direction is exactly equal to the precipitation out of the solid salt. So aqueous ions in equilibrium with their solid is called a dynamic equilibrium. If there is not much solid, it will all dissolve. As more solid is added to the solution, it will become saturated. The term saturated means that particular volume of water is absolutely holding as much as it possibly can of that dissolved salt, and if I added any more, it would just simply sink to the bottom. Thinking about, for example, Kool-Aid, how horribly hard it is to get that last little bit to dissolve, it is creating a saturated solution. So the solid will precipitate as fast as you can get it to dissolve, and therefore we call it a dynamic equilibrium. The process of going into solution is indeed equal to the process of falling out of solution. So if we think about a general equation, if M positive stands for any metal, cation, somebody's first name in an ionic salt, and the non-metal, NM negative, could stand for non-metal, stands for whatever anion. So if I think of a metal with a subscript little a, to a non-metal with a subscript little b as a solid. Metal to non-metal, any ionic compound, we commonly call these salts or formula units. Metal to non-metal, where we use their charges to determine the subscript crisscross to create an equilibrium. So here's what we have. The number of ions of metal dissociate, and I'll just put a positive charge to remind us that metals carry positive, plus the subscript that was on the non-metal becomes its coefficient and it will become negative. We have aqueous ions on the right, a solid ionic compound on the left, and as we begin to think about a process of dynamic equilibrium, an ionic salt dissociates to form its ions. The subscripts then become the coefficients on the product side. The process of dynamic equilibrium is simply a dissolving process of physical change. If we wanted to express this equilibrium in terms of an equilibrium constant K, we have practiced for months now, knowing our journey began with Kc for the concentrations, Kp for pressure, Ka for acids, Kb for bases, Kw for water. This one is now given a symbol of Ksp, the solubility product constant for a dissociation of an ionic compound in water. It's telling us the saturation point. Solubility product, in my head I always think saturation point. How much can actually dissolve in water? But the formula for equilibrium still remains the same, products over reactants. But recall, pure solids and pure liquids do not appear in an equilibrium expression. So we're simply looking at the metal ion raised to the power from its coefficient times the nonmetal ion raised to its power from the coefficient. There is nothing to set that over because the ionic solid does not appear in the equilibrium expression. Pure liquids, pure solids drop out. So we've developed the expression for any ionic compound as it dissolves in water. The KSP is equal to the positive ion raised to its coefficient, which came from the subscript originally, times the nonmetal raised to its coefficient, which came from its subscript originally, the KSP. This is called the solubility product for each compound. The solubility product for an ionic compound as it dissociates in water is simply the metal raised to its coefficient, the nonmetal raised to its coefficient, the solid drops out. It says, watch out, solubility is not the same as solubility product. Solubility product is an equilibrium constant, and we have become very confident to say equilibrium constants have no units. It will not change because it is a constant except if I change the temperature. So generally you'll see KSPs reported out at 25 degrees Celsius. We understand that as an equilibrium position changes with the temperature. So equilibrium constants, no units. A solubility is an equilibrium position for how much can dissolve. In other words, it will have units. Usually it's reported in grams of solute per 100 mils of water, or another common unit might be molarity, moles per liter of solution. So thinking about what might affect an equilibrium position, for example, from our first section of our chapter 17, a common ion can change this. For instance, if I had in solution a positive ion that was in common with the metal, we know according to Le Chatelier it would shift left, pulling some out of solution. I can change the amount in solution that's dissolved by adding a common ion, and we practice that with our first section. The constant remains the same, but the solubility could change if I change things like a common ion, or I simply change if I dissolve it into acid, for instance, or into pure water, things that could manipulate the amount of concentration. That's the solubility part. The constant is always the same. Let's take a peek at an example to help us make sense. Calculating KSP from solubility. It says we have some solid silver chromate added to pure water. Silver with its +1 charge. Chromate is our polyatomic ion Cr(O4), and it's a -2. So when I think about the first sentence, I'm just getting my idea of what the salt is. Silver chromate, Ag2Cr(O4), where the metal ion is a +1 and the nonmetal polyatomic ion is a -2. And I add some of this to pure water at 25 degrees. Some of the solid remains undissolved at the bottom of the flask. This is simply telling me that the solution is now saturated, that I've added so much, it all has dissolved that possibly can, and anything that there's no room for is sitting there at the bottom. No matter how much I stir, I can't get it to dissolve. So some of the solid remains at the bottom of the flask is it's the story problem's way of just telling us we've created a saturated solution. And we've even stirred it for several days to ensure that equilibrium is achieved between the undissolved silver chromate and the solution. So putting that into terms of a formula, what we're seeing is those two ions of silver have completely dissociated, and the chromate is now into solution. The solid is in dynamic equilibrium with its aqueous ions. And it took several days to ensure that, so that's a lot of stirring. Analysis of the equilibrated solution shows that its silver ion concentration. Silver ion concentration is 1.3 times 10 to the -4th molar. Silver ion give us 2 in molarity units. Assuming that silver chromate completely dissociates in water and that there is no other important equilibria involving those two ions in the solution, in other words, no common ion effect that's going to interfere, calculate the KSP for this compound. Well, thinking about what the equilibrium is showing us, let's just begin by writing the expression for KSP. KSP will be shown by taking the concentration of the silver ion squared times the concentration of the chromate ion to the first power. Ions over product, or ions are the product. We simply drop out the solid salt. It will not play a role. What we can use is our stoichiometry skills to figure out the molarity of the chromate. We see that there's twice the number of silver ions as compared to the chromate ions. And when we think about stoichiometry, I'm just going to cut that in half and decide what my concentration is there. So let me find my calculator. We will hit 1.3 E negative 4 divided by 2, and that shows me a concentration value of 6.5 times 10 to the negative 5th for the chromate. And we're just going to plug it in. If KSP is the concentration of silver 1.3 times 10 to the negative 4th squared from that coefficient times 6.5 times 10 to the negative 5th molarity units for both of those, that will generate our equilibrium solubility product constant. We will hit 6.5 E negative 5 times 1.3 E negative 4, and we'll need to square that. And I find an answer 1.098. Let's tell you that's 1.1 times 10 to the negative 12th. 1.1 times 10 to the negative 12th is our solubility product constant for silver chromate. Again, no units on KSP. Let's flip the page and see our next example. Another practice. A saturated solution of magnesium hydroxide in contact with undissolved solid is prepared at 25 degrees Celsius. That first sentence is just simply ensuring us if it's undissolved solid, that's their way of just confirming that that solution is indeed saturated. Magnesium hydroxide is in dynamic equilibrium with its ions. Magnesium ion, now aqueous, and 2 units of hydroxide ion, also aqueous. The pH of our solution is found to be 10.17. So what that can show us, 10 raised to the negative 14 minus 10.17 can give us the concentration of hydroxide. Assuming that magnesium hydroxide dissociates completely, there's no other competing equilibria, no common ions, anything to consider, just the straightforward equilibrium, we'd like to calculate the KSP for this compound. Well, let's begin by hitting out for the concentration of hydroxide. 10 raised to the negative, 14 minus the pH to pull out hydroxide. 10 raised to the negative 14 minus 10.17 flips the pH into the POH for our solution. I hit 1.5 times 10 to the negative 4th molar units. 1.5 times 10 to the negative 4th molar units is the concentration of hydroxide. Again, using our stoichiometry, we can also pull out the magnesium ion with its 1:2 ratio. So I'll simply divide that by 2 and find 7.3, maybe I should say 7.4, rounding better, times 10 to the negative 5th molar units. So with this example, we were able to pull out from the pH the concentration of the base ion. With the stoichiometry, want over given, 1/2 of that value found magnesium. The KSP can simply be found by taking magnesium's concentration, 7.4 times 10 to the negative fifth raised to the first power, times the concentration of hydroxide, 1.5 times 10 to the negative fourth. See that coefficient? It will need to be squared. KSP, let's see, I have 7.39, so that I'll just go times 1.5 E negative 4 squared, and our KSP constant comes out to be 1.62 times 10 to the negative 12th. 1.66 if I carried those decimals. There's a repair. So with this practice, we used the pH, found hydroxide. From that, we cut it in half to find magnesium and just plugged it into the expression where the coefficients became the exponents to the power of concentrations. Suppose we are being asked to calculate solubility from KSP. Solubility is telling us how much dissolves. KSP is the equilibrium constant. So let's take a peek here. We have a KSP for calcium fluoride is 3.9 times 10 to the negative 11th at 25 degrees. So here's what I'm thinking is I'll just reread that first sentence. Calcium fluoride, CaF2 based on charge, is in dynamic equilibrium with its ions, Ca plus 2 and 2 fluoride ions. Again, when it dissociates, 1 calcium is produced, but 2 fluoride ions, the solid in dynamic equilibrium with its aqueous ions. And they're providing for us a KSP as 3.9 times 10 to the negative 11th. Assuming that calcium fluoride dissociates completely, there's no other important equilibria affecting its solubility. And that's placed in the problem to just tell us there's no common ion effect, which would affect solubility. We're being asked to calculate the solubility of calcium fluoride in grams per liter. Grams per liter ends up to be our target. So, if I think about what this expression is telling me, we're asked to find ultimately how many grams per liter of this solid salt is dissolved. Let's take a peek at what the expression is showing us. If the KSP is indeed the concentration of the calcium ions in solution times the fluoride ions in solution squared, and this value is provided for us, why don't we call the value of calcium ion X and the value of fluoride ion 2x. We can set that equal to the known KSP value. So here's what we have. 3.9 times 10 to the negative 11th, the value of KSP provided, is equal to X, what we called calcium. The value of fluoride is 2x, and I need to still square that value. 3.9 times 10 to the negative 11th, and let me just simplify that. 3.9 times 10 to the negative 11th is going to be equal to 4x cubed by the time I'm done simplifying this algebra on the right-hand side. 4x cubed. Alrighty, so why don't we just pull out x with our calculator. 3.9 e negative 11th. That's 44. There's the 11th. 3.9 e negative 11 divided by 4. And that's equal now to x cubed. Raise that now to the value of cube root. And we get 2.13, and I'll carry that over. X is equal to 2.136 times 10 to the negative 4th. And what X is standing for is the calcium ion, so there's a molarity unit there. However, since the ratio here of the salt also is 1 to 1, what this number is also telling us is 2.136 times 10 to the negative 4th molarity units is the calcium fluoride concentration in molarity units. So if we know 2.136 times 10 to the negative fourth molarity is equal to x moles per liter, and that's really what we're trying to solve for, is per liter. This value is also the number of moles, and moles times molar mass will pull out the number of grams per liter. Let me add a molar mass for calcium fluoride. We have 40 from the calcium, 19 times 2 on the fluorines. Molar mass is 78 grams per mole. Alrighty. So let's hit for the answer. We have 2.136 e negative 4 times 1 gives us moles. Moles times molar mass, so times 78. And we find our answer, 0.017 grams per liter of calcium fluoride. Revisiting the journey, we set up our equilibrium constant expression as being the calcium ion times the fluoride ion squared. I like to select the value for x, the ion that has just 1. So x became calcium, 2x became fluorine, and we squared. Our KSP then was equal to 4x cubed. Doing the algebra, we pulled out x. X represented originally the calcium ion concentration, but due to the stoichiometry, it also represents the calcium fluoride concentration. From there, we did some molarity work. Molarity times volume pulled out moles. Moles times molar mass pulled out the solubility in grams per liter. The last problem we will work that will complete our note pack. Another try. The KSP for LaF3 is 2 times 10 to the negative 19th. What is the solubility of lanthanum fluoride in water in moles per liter? So up above we had to do grams per liter. Here we're doing moles per liter. That's what molarity is defined as. So lanthanum fluoride, LaF3, is in dynamic equilibrium with its ions. Lanthanum, who must be a +3 charge, and 3 fluorides, which are -1. KSPs are either found in our Appendix D or provided in the problem, 2 times 10 to the negative 19th. Quite a small number. This must not be very soluble. I would expect quite a small answer. So here's the expression. If KSP is equal to the concentration of the positive ion raised to the first power times the concentration of the negative ion raised to its power of 3. Why don't we call lanthanum X? Fluoride will have to become 3x, and we'll set that equal to the KSP constant. 2 times 10 to the negative 19th is equal to x, that's the lanthanum value, 3x, that's the concentration of fluoride, and it needs to be cubed. So we have x times 3x cubed. Simplifying, 2 times 10 to the negative 19th, let's see, 3 cubed is 27. X cubed times x, this gives us 27x raised to the 4th power. Let's hit with our calculator, pulling out x. 2e negative 19 divided by 27 sets that equal to x raised to the 4th power. So let's take that answer and raise it to 1/4 power, pulling out just the value of x. And x is now being shown as 9.28 times 10 to the negative 6th molarity, big M. Those brackets are big M. And that's the lanthanum concentration. The x was given to La+, but notice the stoichiometry is still 1 to 1. So this is also representing LaF3, the concentration of that original salt. It wanted it in moles per liter, and that's what molarity is, so there's the value that we needed. If it had asked for grams, it did not, but if it did, just the next step would be to multiply by its molar mass, and that would convert it into grams per liter. The molar mass value of 195.9, And we come up with a quite small number that we had anticipated, 0.0018 grams per liter of LaF3. I'm only showing that to just review. If it asks for grams per liter, it's just an additional step where we use molar mass to convert moles into grams. This problem did say to stop at moles per liter, which was the value of X. That concludes the KSP in our notepad practice.